Okay, great. I think we've got a quorum here to get started. I am really excited for this webinar today. The webinar is going to be given by Alfonso Ladino Rincon, our fantastic summer intern. But before Alfonso gets into his webinar, I'm just going to give a short introduction to Earthmover, what we're doing, provide a little context, and then we'll turn it over to Alfonso. So, Alfonso, you want to jump to the next slide? Great. So,
Sure.
Welcome, everybody. We are Earthmover. We are a public benefit corporation, and our mission is to empower people to use scientific data to solve humanity's greatest challenges. So we're a group of scientists, engineers, and software developers who have come together to try and move forward the state of software and data infrastructure to make it easier to work with Earth system and scientific data at scale. Next slide, Alfonso.
Sure. Oops.
We really got our start in the open source scientific Python community, working on tools such as Xarray. That's how I met my co-founder, Joe, and I can see quite a few Xarray developers here on the call as well. We got interested in the storage game, working on Zarr, a library for multidimensional array storage. And then more recently, we've released IceChunk, our transactional tensor storage engine that works with this whole stack, provides a database style experience for working with multidimensional array data in the cloud. And so these tools are really widely used throughout environmental science, including meteorology. And today we're going to hear about how they have been adopted for the radar data space. Next slide. In addition to our open source, our product is the Earthmover platform, which you can think of as a full stack data management solution with an open source core built on the tools that I just described in the previous slide, but that really enables organizations to go from 0 to 100 in terms of storing, managing, and querying multidimensional array data in the cloud. So we do this by layering on top of cloud object storage, providing Array Lake, an object storage-based data governance layer with data catalog, data governance capabilities, and then Flux, our API gateway that serves up that data through a range of standards-compliant API protocols and allows you to flow that data into all kinds of different apps, dashboards, etc. So this is what we're doing at Earthmover. Next slide. Our customers are folks, teams of all shapes and sizes who are using environmental data to build data products and deliver value and solve, challenging problems in terms of risk, weather forecasting, insurance, energy, using this type of data. And we are hearing an increasing amount from these folks about radar data, the desire to use radar data for all kinds of different applications. And so, this really caught our attention. Next slide. We're interested in radar data because we think it's a great example of a sort of foundational, data type that is really well served by the multidimensional array data model. So our core thesis at Earthmover is that there are all these data types that don't fit well into the standard relational or tabular data model and that need the richer, more complex data model expressed by Xarray in order to really build satisfying workflows and efficient data systems. And so tensors or multidimensional arrays are found throughout computational science, from geospatial to bioimaging and neural imaging to all kinds of simulation domains, fusion and energy, and certainly used heavily within deep learning and machine learning community as well, where they're called tensors. And so radar data is a really interesting instance of this because it's generated by a very complex instrument with a very intricate sampling pattern that requires a lot of specialized knowledge to interpret. And so we've been really privileged to have Alfonso working with us over the summer to help us improve the way radar data are stored and queried building on a lot of great work that's happening in the open source and the Pangeo community. So with that, I want to hand it over to Alfonso Ladino Rincon. Alfonso is a PhD candidate at the University of Illinois Urbana-Champaign, and he spent the summer with us as an intern. And so this is, in many ways, a capstone of the work he did this summer, and we're really excited to hear from him. So Alfonso, take it away and dive into your talk.
Okay, Ryan, thank you. Hi, everyone. Today I'm excited to share the advancements that we have made during my summer internship at AirMover on improving the management of weather radar data. We use FAIR principle and cloud-native solution to make the radar, the data, of course, more accessible, efficient, and impactful for both science and decision-making. Yeah, I've been working with radar data for around a decade, and then I've learned that not always the hardest part is the science, but sometimes it's the data most of the time, I would say. By the end of the talk, I will help you will see how we can go from millions of fragmented files into a fully structured, crowd-optimized data set, ready to power long-term research, real-time insights, and also machine learning applications as well. So first, let me introduce myself. I'm Alfonso Ladino. As Ryan already mentioned, PhD candidate at the University of Illinois. I am a data scientist with about more than 10 years of experience with active and passive remote sensing, from ground-based to spaceborne radar, as well as in situ measurements or instruments for studying cloud and rain microphysics. My work focuses mainly on improving rainfall estimation using both machine learning and physical models. I also contribute to open source projects, Python projects like Xarray, NEXRAD, and Project Pythia. So let's jump to the presentation. So yeah, okay. Before we get into the data challenges, I want to quickly show how weather radar works, especially if you are not coming from a meteorology background. On the left, you are seeing a radar in operation, spinning 360 degrees at a fixed elevation angle, collecting data like reflectivity, which most of the time help us to see precipitation. After one sweep, the radar tilts up the antenna to a higher elevation and repeat this over and over, building a full 3D slice of the atmosphere that we call volume coverage pattern, or VCP. This VCP happens every few minutes, delivering high-resolution continuous measurements, ideal for both real-time and long-term operation, if we manage the data properly. And so on the right side, and this is the kind of application that we want to see, you can see the radar reflectivity animation of the Hurricane Dorian approaching to the Florida Peninsula. The radar tracked the storm structure in real time, showing the right bands, the eye wall development, the intensity changes, and that information is quite critical for forecaster and emergency manager in the moment, but also is an important information, valuable information for climatology studies once the data is archived. So as I just mentioned before, radar data is usually used in two different workflows. The first one is in near real-time application that supports severe weather detection, storm tracking, tornado detection, aviation safety, and more. And the idea here is to transform single raw files into actionable insights almost instantly. At the same time, the raw data is archived in cloud buckets, local data centers, or even tapes. And the key part here is that they usually use legacy binary formats. On the other hand, we have the long-term application, which turns archival observation into insights, for example, for agriculture, machine learning, water resource planning, and more. And here is the problem. These applications are limited by how we store the data. Instead of having or being a unified structure format, we have an scattered, or the data is scattered across millions of standalone files, each one representing a single volume scan. Often, most of them are not climate forecast convention compliant, CF compliant, and some of them are locked into proprietary binary formats. And because the lack of a structure, there is no way to query or subset the data, as Ryan mentioned at the beginning. So therefore, scaling radar analysis means that we have to rank with millions of proprietary binary files one by one. This creates a lot of issues when we are doing long-term applications. So the result is a huge barrier between the data that we have and the products that we want to build. If we zoom out for a moment, we can realize that this challenge isn't just a US problem. This is a global one. According to the latest World Meteorological Organization radar database, there are more than 800 operational radars around the world in around 90 countries. And together, all of them scan a lot of the atmosphere in detail every few minutes. So we have between 5 to 10 minutes scanning all of those radar. However, while the physical coverage is vast, the access to the data is not. So when we apply a filter for open data, the maps shrink dramatically. So as we can see here, only 3 national network provides any kind of open access to this data. Those are the US Radar Network, the FMI Finland Radar Network, and the Colombian Radar Network. So together, they all represent less than the 20% of the world operational radars. And now the question might be the rest. Well, the data might exist. It might be restricted offline or buried in a hard-to-access archive. If we focus now in the US radar network, this is one of the most comprehensive and long-term running system in the world, and also an incredible results. But also, it's a perfect example why open data doesn't always mean easy to use. Thanks to the NOAA Big Data Partnership, in 2016, the full NEXRAD Level 2 historical archive was made available in Amazon, covering data from 1991 to 2016. They released roughly around 270 terabytes of data with 180 millions of files. So arguably, this is a lot of information. And then if we fast forward to this year, to February of this year, the archive has grown to roughly 870 terabytes. I would say that for today, it should be around a petabyte with around 360 millions of files. So I guess, and I'm totally sure, this is a treasure trove for meteorology, climate research, and also data science. But here's the catch. While the data is technically accessible, it is still not very compliant, which means that it's stored in random and raw binary files. Those files are isolated, not interconnected, and difficult to reuse. So that means that we have barriers to access, we have to duplicate effort and unnecessary complexity even for basic reproducible analysis. In short, the data exists, but it's not easy to use, and what is limiting the very promise of open science. The key reason why the radar data remains fragmented is the operational complexity introduced by the VCPs. Basically, here in the US, VCPs adapt the radar scanning strategies to the current weather condition, for example, clear air versus precipitation. So here you can see 2 radar. One is scanning clear skies, the other one precipitation, and their strategies are totally different. They are completely different. In precipitation mode, radar might scan up to 19 elevation angle, even more, starting low and building a detailed observation of the vertical profile of the storm. In contrast, in clear air mode, the radar only might scan few angles, and this scanning strategy is optimized mostly for detecting weak echo returns like atmospheric boundary layers or biological targets. So this variability is ideal for real-time operation, but for anyone which is building a long-term data set, it means that each file can have different structure, different number of files, different number of sweeps, different number of angles, and an inconsistent vertical resolution. That's why simply stacking these files together doesn't work. We need a data model that can handle this complexity. And that's what I'm going to present today. So this leads directly to the core challenge I explored in my first blog post. The first conclusion that I have is we need to rethink the way that we manage radar archive, the way that we archive the data. So this blog post, pulls together everything we have just covered down to here, from archive fragmentation to structural variability caused by the VCPs. So the question now becomes, how do we bridge the gap? To answer that question, the World Meteorological Organization endorsed the FM 301, a global data standard for radar and LiDAR data, initially released in 2018 and finalized in 2024. It builds on top of the NEXRAD format and CF convention, and it organized single radar files into a hierarchical data model with 3 different levels as shown in this diagram. So at the root level, we have the global metadata and ancillary variables. At the node level, we have the sweep grids for each tilt with the sweep-specific metadata. And then finally, at the leaf level, we have the actual measurements for it, the measurements like reflectivity or radial velocity. In 2024, this standard became way much easier to use, and it was implemented in the Xradar library in Python, which was built on top of the Xarray and the latest DataTree data model. Although we have a data standard, it is still file-based, which means that large-scale analysis is difficult and remains difficult to manage because we need to still handle with files, like single files. So we need an extra layer on top of this one for more structure. So if you want to read the full history about the FM301, including the origin, structure, and how this was implemented in Python, I've just covered this in this blog post. And the key takeaway is that the FM301 data standard makes individual radar and LiDAR files self-described and interoperable. And then for sure, the most important thing, I guess, from this is that now we have a structure, but this structure is still, again, for a single file. So to further improve the management of this, of multiple files, we developed something that we call the Radar DataTree model. This is a hierarchical structure that unifies radar scans into a coherent, scalable dataset. So with this animation, I will try to explain how this data tree works, or it was built. And it starts with a bunch of radar files stored in the cloud, millions of them, each of them represented by a single BCP. And using an extraction, transformation, and loading process, we load and organize these files into a hierarchical data tree where each node corresponds to a specific BCP. This preserves the unique geometry and metadata of each file. Within each BCP node, now if we get in an extra level, all these scans are going to be concatenated along the time dimension, creating a fully navigable query-ready time series for each scan pattern. So once the data is structured in this way, using this hierarchical structure and lives within the Xarray domain, we can just easily export to Zarr for analysis-ready and cloud-optimized storage, and leverage IceChunk transactional model for safe version and collaborative dataset updates. This not only makes radar data more efficient to store and access, but also it ensures our radar data tree is fully FAIR compliant and support async transaction and data versioning control. I guess this is one of the most important points here. So now that we have a data structure for our radar data, we can start doing the real science. So one of the common application or powerful analysis is the quasi-vertical profile introduced by Riskolf et al. In 2016. So basically, this technique, what it does is extract the vertical storm structure by averaging the data along a constant elevation angle, usually is 20 degrees, across the full 360 sweep. The result is a vertical profile of the atmosphere above the radar side, revealing features such as melting layers, hail cores, or storm evolution over time, as shown in the figure in the right. To test our data tree model, we use radar from the KVNX Oklahoma NEXRAD radar over a 2-hour period in May 2021 during a severe weather event. So although we are going to analyze or we are going to reproduce this image, we ingest a full month of radar data, as you will see. So yeah, I guess I already explained you what is the problem, what is the solution with the radar tree, with the radar data tree. So I'm going to just jump into the radar demo. So here we have a radar demo. Could you, Margaret, or one of the team, share the link to the...
Will do, Alfonso. Yep.
Thank you. So I will share the link to the demo in case you want to reproduce this. And then the idea is to showcase the radar data tree. So at the very beginning, we know the problem. We have millions of fragmented files, difficult to access, difficult to process, and then the solution is radar data tree, which allows us to give a structure. So this demo is going to be structured into parts. The first one is the old way. I'm going to just show how those files, individual files, looks like, and then the second is introducing you the radar data tree. Before I start the demo, I would like to let you know that I create a demo function that you will also see in the repo, in the GitHub repo, where I have put multiple functions that I will use during my demo. And then, yeah, the idea is to keep the demo simple without like too much lines of code. So if we go back, the first thing is, as I just mentioned, It's the old way. So here is basically file by file pane. We have individual files. Oops, sorry. We need to, and this is something that we don't have to do anymore with this data tree model, is that we need to download the data locally and start processing, which creates data duplication. We have to do manual alignment. Not all the time that you download all the single files, all of them are going to correspond to the same BCP, which means that you have to do alignment, things like that. You have to create custom pipelines, memory management, and then of course hours of processing. So I'm just gonna list of the NEXRAD files that we are gonna find within May 20th, the full day. And then if I execute this, it's gonna say that within this folder in the NEXRAD S3 bucket is gonna be like 320 files. All of those files having this structure. This for sure is it's just a path, but that this reveals how the data is stored. It's a single files, compressed files, not interconnected, not queryable. Basically isolated archives. In total, we have 320, as I just mentioned. We have, and now we can imagine if it is multiple days, multiple raters, or even long-term statuses. This is going to be a really huge problem, and it's basically because it's going to be a I/O bounded problem. We need to open a lot of files. So now, here is this is my conclusion is. This is why radar data science has been so challenging. It's because it's difficult to handle the data. So now let me introduce the radar data tree. But before we dive into the code, let's explore. As you might already know, Earthmover is the Array Lake platform, which allows us to see the data visually in their dashboard. So this is the Array Lake platform. Here is the QVNX repo, and then within the QVNX repo, we have subgroups, multiple subgroups that we have built for this radar data tree. So as I just mentioned, we have multiple BCPs, in this case, 11 to 32. And then, yeah, we can just click here to get into one of those BCPs. As if you remember, we have this FM301 data standard, so it's going to be BCP, it's going to be then sweep, the sweep level, and then within the sweep level, we have the variable level. So here we have all the variables. And then if we click here, we can see things like what are the dimensions, the shape of those dimensions, the data type, as well as attributes following the climate and format conventions. So I think this is one of the most important things, and thanks to Array Lake, thanks to Earthmover, is that we can have within our data set a version control. We can have a snapshot, and every time that we write that ingest a file, we can have a control or a snapshot that allows us to roll back in case we create some sort of like data corruption. So this allows us to keep the data safe. And thanks for doing this, which is amazing. Okay, yeah, some metrics and then other settings, but I'm just gonna stop here and then coming back to our radar data tree. So the first thing that I'm gonna do is to connect to the Earthmover cloud platform using the Array Lake client. Just gonna log in. I already went through this process, so I'm just gonna collapse or contract this. I'm just gonna create a read-only session to the QVNX repo. Read-only session, I went ahead and I already ran the Coiled cluster, so I wanted to be ready for the demo. So I'm not gonna run this again, but I'm gonna get the client now. So now we have a client, and here is where the magic happens. So I'm gonna go to open the QVNX radar data tree with 1 month of data across multiple BCPs. So I'm just gonna import Xarray, and as you can see here, it's just one line of code. Xarray.open data tree, and then the other are just parameters. I'm gonna execute this, and this is gonna take around between 14 to 20 seconds. And this will be faster as soon as there are some ongoing work in the Xarray library. So we can notice, and we found that when we were creating this data tree, we found that open data set in Xarray is doing sequential looping when doing GET requests. So now we are implementing, or the core development team in Xarray is developing an async or concurrent approach. So this will take nearly in the future a couple of seconds. Although it is taking around 20 seconds, it is just a tiny part of the, if we could imagine like processing like around 6,000 files that we will find within this month. So this is basically nothing. So let's keep going on. So now we have our data tree loaded in memory, as you already might know. This is not We haven't downloaded any data yet. It's just metadata, so we can have an in-memory representation of this. So let's check how this looks like. So here, as I just mentioned, we have an Xarray DataTree that for this case have 5 groups. So again, no more files. Now we have groups. And then within each group, we have BCPs, as I just mentioned. And then within BCPs, we have the node group. And then within the node group, we have the data variables, as I just mentioned. So we have in total, let me show you, the size of this data set is around 765 gigabytes. This is not super big, but still this is just 1 month of data. So if we could imagine this for, if we multiply this for 160 radar across the US, and then for around 25 to 30 years, so this is just basically just a small piece, but still is considerable size. We explore what we have inside. So we have inside, as I just showed you in the Array Lake platform, we have 5 BCPs. Each one is organized with multiple timestamps. Radars can just showing the start and end time. We have May 1st till May 31 of 2011, and then let's start exploring this data tree. So we can access the data tree by using dictionary notation by key value. So we are going to say from my data tree, give me the VCP to 12 in this case, and give me all the sweeps that you are going to match within this data tree. So if we hit this, the result is going to be around 17 sweeps. We can change, I don't know, let's say to 32. And this is going to be like just 6 sweeps. So if you remember, if you recall, I talk about like pressive mode, or clear air mode, and then here is like, this is a clear air mode. So of course, we can also access directly to each sweep by passing a file path syntax and then just requesting the data set. And then this will give us, again, a data set with the radar dimension as well as the VCP time dimension. So this is the one that will allow us to do queries over the time. Yeah, for sure. We have coordinates. We have coordinates. We have all our data variables within this data set, and then also indexes and attributes, as we already are familiar with this. And then finally, we can actually have an access directly to the data. So just passing this path. In this case, I did 212, but it could be 12, or it could be either 11. And then, yeah. What it is going to do, and as I just mentioned before, we have only metadata, which allows us to have in-memory representation. Again, we know the chunk size, so the data is chunk for efficient analysis and subsetting, also for scalable analysis. We can use a cluster to compute this, and then coordinates, variables, and then what I wanted to show you is the attributes. We have the CF climate format conventions. So now we know this file is self-described. We know what is inside this. So I guess this is at least for me, I've been working with radar data. This is one of the most important feature of this is that we can do effortless time series navigation. So instead of going one file by one file, I can just target the severe weather event that I want to say. Let's say starting on this date, 8:30 in the morning. It's not in the morning. This is UTC till 12:30 UTC, and then I can just query the data using the .cell method that we are used to use. So let's see what happens if I do, hey, give me this slide of time, and then this will return me a new data tree. But in this case, I've just while selecting this time range, it will just return me one data tree node, which is the BCP 12. So now we have the same, again, conserving the same FM301 data standard. We have BCP, we have groups, and then within groups we have data, and then all of this is climate for my compliant. Let me collapse this, and then here is where the fun begins. So we can do plots or do interactive storm evolution using the HP plot Python library. So again, this is just one line of code. I'm just going to access the reflectivity, the horizontal reflectivity data. I'm just going to do a quad mesh, and then the rest of the parameters are just function parameters. So here, this will take a couple of seconds, around 6 to 7 seconds. And then, yeah, the data here is being streaming. So I don't have to download any data in advance. So after I just I did the query and everything I wanted, it will just start downloading the data. And then, for example, here I have the opportunity to do looping animations and things that I can even go further. I increase the velocity. And then, yeah, I am using the sweep number 12, but I can do lower. Let's do sweep number 0. Again, this is going to take around 6 seconds downstreaming data, fetching data. But now everything is analysis ready. So it took like less, actually. So here you can see, again, this animation, radar reflectivity for this event. We can do zoom in. We can check what is happening within this. And then, yeah, we can play with the data. We can do actually the signs. So now it's time to do the real science. So the idea is to do the quasi-vertical profile, as I just mentioned before. So I'm just gonna compute the quasi-vertical profile for the period, the time period that I just mentioned, from 8:30 to 12:30. I'm gonna use one function that is called QVP from the demo function that I just mentioned to you. I'm gonna pass the data set and the variable for which I want to compute this QVP. So it's gonna be reflectivity, differential reflectivity, cross-correlation ratio, and also differential phase. And this is going to take around 4 seconds. So I couldn't imagine doing this like by downloading file by file. So this is quite fast, 3 seconds. And then now we just have to do is plotting the data. This will take milliseconds. And then here we have successfully reproduced the QVNX, the quasi-vertical profile from Richkoff et al. 2016. So yeah, we can go even further. I want to do quantitative precipitation estimation. This is one of the most common application in radar data, is transform radar reflectivity into rainfall rate. That is what I've been working for the last 10 years. And then what we usually do is use a CR relationship. So a relationship that can convert from reflectivity to rainfall rate. And then, yeah, I can do it for the full, for example, to 12 BCP around the lowest elevation angle and the reflectivity variable. This is going to be 416 BCP, so we are going to compute 416, and then I'm going to accumulate it. So I'm just going to collapse this, or yeah, if that is the name, and compute the full rainfall estimate using this method. So let's do this. This will take nothing, because until here everything is just lazy loading, and that's doing the graph. But we are going to do a quantitative precipitation estimation over 4 days and 17 hours. So this should take, like in the traditional workflow, downloading data, putting everything together, arranging everything I already mentioned, but now it's like just querying the data, like right straight forward. So this is how the data looks like now. We have just one slide. Now we have compute the full rainfall, rainfall depth, the accumulation, and then now we can hit dot plot, and here is where the data streaming is going to start doing their work. Like we are fetching now the data, and then after 3 minutes, we can have the estimate for the 4 days. So this is quite interesting image, because as I just mentioned, you have Precip mode and also clear air mode, but within Precip mode, you have something that is called the severe weather mode. So into 12 mode, you basically try, or you want to try to track the tornadoes. And what you are looking here, all of those lines are supercell storm that might at some point be, or might have been tornadoes. So as you can see here, we can see the way that we're, or we can think in a long-term studies, we can see actually the storm tracks, right? I'm just gonna go ahead and come back. I'm just gonna do the BCP12, which is a little bit more, just for the demonstration. This is just gonna be 806 BCPs. Again, we are gonna do the same, and then just to make sure, to show the difference to you while computing this. So instead of doing 4 days, now we are going to do 17 days of quantitative precipitation estimation. And this is going to take 6 seconds in total. And now we have a total different pattern of precipitation. So now the radar was measuring total different weather. And here it's interesting to see that within 17 days, we have more than 160 millimeters, which might be nice for weather resource planning, for flash flood forecasting, and other applications. So yeah, with this, hopefully I show you the power of this DataTree data model. We went from around roughly 6,100 scattered files of 1 month of data to just one unified data set, from hours of processing to seconds to science. We went from custom ETLs to 3 lines of codes, roughly. We went from file hunting to direct path access. So yeah, I just computed the QVP, the performance improvement. I put like a 100 times faster, but I feel like it could be even more. And I guess my final conclusion for my demo is that this is more just than a technical improvement, it's a shift of paradigm. So we are now able to do the real science. So with this data tree, I guess I'm totally sure we enable the reproducible research. We can open the doors for doing machine learning over radar data, as well as collaborative science. And this model applies for both the real-time and long-term operation. So yeah, I guess I'm finished my demo, and I'll be back to my slides. So, okay, I'm gonna transition to my conclusions. So first, Radar DataTree model transform radar archives into a structured, fair, compliant data set, making them both accessible and impactful for science and decision making. Time series organization within data trees enable fast scalable analysis with minimal input-output operation, as you can see. As I already showed to you guys, well, this meaning that this decrease or totally cuts the processing time from minutes to seconds. Our ArcOffer storage with Zarr and Ice Chunk might involve some data duplication. So unfortunately, the downside of this approach is that we need to duplicate the data. We need to create a new data set. But I think it delivers a huge gains in terms of accessibility, reproducibility, and workflow efficiency. I guess this is the most important conclusion, is that we can use now iChunk transactional versional data model that ensures safe collaborative updates without corrupting the data. And finally, while today's example was for radar data, this model works for LiDAR data, and also it can work for real-time operation or long-term applications. So with this, I will transition to the acknowledgement. So I want to thank the Earthmover team for their support and collaboration during my summer internship. This project wouldn't exist without their expertise and encouragement. The picture here is with part of the team at the Cloud Generative Conference. Not everyone could be there, but I'm grateful to all of them for their time, guidance, and ideas. And I'm also grateful to my advisor, Steve Nesbitt, for his guidance, and also to the Open Radar community for building these tools and standards like XRadar, and that made this work possible. So with this, I will finish my presentation, and I'll be happy to take any questions.
All right. Thank you, Alfonso. That was really awesome. Here's how we can do questions. I see there's a lot of chatter in the chat. Feel free to use the question Q&A feature within Google Meet if you want to type a question, or if you want to just raise your hand and go on camera and speak up and ask your question here live. That's fine too. Whatever people want to do. So yeah, do people know how to find the Q&A feature? Is that obvious? I think it's over in the meeting tools. So yeah, I see someone making some comments in the chat, but okay. Yuri, go ahead.
Hi, Alfonso. I think that it was a great work that you're presenting here. My question is, how do you think that this new architecture could change the data assimilation for weather models?
Yeah, okay. Let me think. I guess the most important part of this is that now you can query the data that you want. It doesn't matter if it is just near real time or long term. So you can either ingest just the latest file, or if you have another kind of model, you can now ingest the full history of the radar file if you want. You can compute climatologists, I'm not a model expert, but if you want to compute a climatology and then put that climatology into the model, now you will be able to probably maybe improve your model or your simulations.
Yeah, I think that I just found that great because I was wondering, I mean, since this is so hard, such a hard data set to handle, I was wondering if it's really already assimilating the models, or if this is going to actually open a new door to these implementations. But yeah, it's great. Anyway, I mean, having this data streaming in a more efficient way, I can see many other applications too. But thank you very much.
Thank you, Yuri. So any other questions?
I posted one on the Q&A.
Oh,
feature.
I didn't see that there. Sorry. Yeah. Okay, Max, why don't you just go on and ask your question live since you're here?
Yeah. So this is really, really amazing. It's great to see XRadar and DataTree applied in this way. My question is related to how should these archives be created and who maintains these? Do you see this as falling on the data providers? So for example, NOAA being the sort of folks who generate a lot of the NEXRAD data, or these different international groups and stuff that are generating this? Do you see it as the role of private companies, the sort of broader open radar community? Like what governance type model or like enforcement of some of these standards and stuff like that do you see?
Thanks, Max. Well, I don't have a final conclusion on this. I guess the data model is there now. We have to talk with the public agencies to see if they are willing to use this one. If not, always we have the door open to either private or public institution to use this. So yeah, I guess the most important thing here is that the open radar community is always here present, and then yeah, we are leveraging on the advancements that we have done in XRadar in the open radar science community, and then try to keep everything working and going on. So yeah,
I guess along those same lines, and yeah, I know Kai has a question as well. Do you see like putting this forward, like sort of wrapping this up into some sort of like white paper or like general paper and stuff like that as a recommendations for providers? Because I could see that being helpful, especially in a journal like the BAM, like the Bulletin of the American Meteorological Society or something like that. Like something where a lot of these data providers are looking to provide their data in a more performant way, but might not necessarily know how, or might not even know. Like I'm thinking back to like the Pangeo paper that Brian and Shell and the rest of the team had sort of put together. Like I'm wondering if it's time for something like that for the great work here.
Yeah, definitely. There are a couple of ideas here. The first one is going to be the DataTree is now being in the process of being a paper. So I'm writing a paper now on this data model, and then for sure the whole workflow could be also published in a white paper as an BAMS or something similar, on a similar journal. Mm-hmm.
Thanks so much.
Yep. Okay.
Yeah. So you mentioned the efforts of WMO FM301, and I see this. This is the way this should be rolled out. So we need the support of these international organizations, so that now we have the standard which we can use, which you use in this package here, and they should put the pressure to the weather services or data providers to directly roll out their data in a kind of accessible like standard like that. That's my impression, at least.
Great, thanks, Kai. Yeah, this year we are gonna be in the AMS Radar conference at Toronto in a couple of weeks, and then we will try to take advantage of that and share this data more. There will be a presentation on this as well, another talk, and yeah, the idea is to talk with the World Meteorological Organization people and try to see if we can go further with this data model, with this Radar DataTree model.
maybe I'll just jump into the conversation. I
Sure.
really like the question that Max asked and Kai is referring to here. Whose job is it? Who should maintain these type of analysis-ready data archives? And we've had a lot of experiments around this within the Pangeo community, right? And it's a really tricky problem. The primary data providers tend to be very conservative and reluctant to change the formatting of how they distribute data because there's so many applications which depend on that. And they're at the same time, they're very hesitant to duplicate data ever. So that's where the virtualization approach, the virtualize-R approach, has a lot of potential to enable them to do that. But there's even something a little bit broader, which is many of these organizations are not really committed to the cloud as a way of sharing data, and if they are, there's big questions about which cloud. Certainly, the idea in Europe that they're going to use American cloud providers to share data was never popular and is even less popular today than it was, 6 months ago for obvious reasons. So, what we see at Earthmover is, private companies are building up very large archives of analysis-ready data. Some cases, storing and reprocessing whole archives, petabytes worth of data to support their operations. But of course, those are proprietary and they're used just internally for their applications. Whenever a university invests in an effort like that, they do it in a way that they want to just benefit their students or their users. They're not trying to serve, the whole community. So, whenever anyone puts money towards this, they kind of want to provide an advantage to whoever their users that they're supposed to support are. So if DOE were to step in, they'd want to do something that's going to support DOE scientists, right? But not necessarily everyone. So it's a tricky problem, and it requires a funder who is really thinking about what's going to be good for science across both private sector and public sector applications, and is willing to do something quite ambitious and innovative. So I personally think that perhaps some of the private science funding agencies, I won't name any specific names, but are maybe some of the best candidates to fund that sort of project because they're not trying to, just benefit one subset of users. They're thinking very broadly, and they're very open to innovation and new technologies and ideas. Yeah, I mean, Dynamical is a great organization, great example of they're attempting a sort of cooperative business model around that, and I think it's definitely worth following. Yeah, someone still needs to pay for it in the Dynamical model, though, right?
Mm-hmm.
And rant. Any other questions or comments for Alfonso?